All right. My eyes. Come on. Sundays, man, I just sleep all day. Ah, ass. All right, you guys. Okay. Okay. Let's check to see if we're live here. Mm-hmm. All right. It's not button this up a little bit. Be all right. Okay. Gotta wake up here. All right, let's just get started without further ado. Okay. Okay, dust, I'll be on in here. Let's let people roll on in. My goodness. My eyes are so dry. I mean, like, all right, everybody. Let's get started here. Get some on my face. All right, let me start with the recording and we'll get going. All right, hello everybody. Welcome back into the channel. Hope you're having a wonderful day so far. My name is Michael. Today we're going to be jumping back into C Programming: A Modern Approach, second edition by K.N. King. We're going to be starting chapter 9 today. Where are you? Alright, we're going to be starting and reading chapter 9 today, functions. So hope you're having a wonderful day and welcome in. This is the condensed version from the live stream. If you want to join us live as we read through the entire chapter and take notes in a more robust and interactive fashion, please do so. Other than that, you can enjoy the condensed read aloud audiobook version here. The notes that you see on the right side of my screen can be found sorry. The notes that you see at the right side of my screen can be found in my Discord. No, sorry. The notes that you see at the right side of my screen can be found within a GitHub repo linked down in the description. Thanks so much for being here, and let's go ahead and get started. In C Programming, a Modern Approach, 2nd edition, Chapter 9, Functions. Okay, here we go, boys. I'm going to try my best to just read fluently here and take our time and just get through it. Chapter 9, Functions. If you have a procedure with 10 parameters, you probably missed some. We saw in Chapter 2 that a function is simply a series of statements that have been grouped together and given a name. Although the term function comes from mathematics, C functions don't always resemble math functions. In C, a function doesn't necessarily have arguments, nor does it necessarily compute a value. In some programming languages, a function returns a value, whereas a procedure doesn't. C lacks this distinction. Functions are the building blocks of C programs. Each function is essentially a small program with its own declarations and statements. Using functions functions are the building blocks of C programs. Each function is essentially a small program with its own declarations and statements. Using functions, we can divide a program into small pieces that are easier for us and others to understand and modify. Functions can take some of the tedium out of programming by allowing us to avoid duplicating code that's used more than once. Moreover, functions are reusable. We can take a function that was originally part of one program and use it in others. Our programs so far have consisted of just the main function. In this chapter, we'll see how to write functions other than main, and we'll learn more about main itself. Chapter 9.1 shows how to define and call functions. Section 9.2 then discusses function declarations and how they differ from function definitions. Next, Section 9.3 examines how arguments are passed to functions. The remainder of the chapter covers the return statement. Section 9.4, the related issue of program termination, Section 9.5, and recursion in Section 9.6. All right, here we go. 9.1, defining and calling functions. Hey Silva, how's it going? Hey Jock, Luke, how's it going? 9.1, defining and calling functions. Before we go over the formal rules for defining a function, let's look at 3 simple programs that define functions. Computing averages. Suppose we often need to compute the averages of the 2 double values. The C library doesn't have a quote average function, but we can easily define our own. Here's what it would look like. Double average takes in a double A and double B. Return A plus B divided by 2. The word double at the beginning is average's return type, the type of data that the function returns each time it's called. The identifiers A and B, the function's parameters, represent the 2 numbers that will be supplied whenever average is called. Each parameter must have a type, just like every variable has a type. In this example, both A and B have type double. It may look odd, but the word double must appear twice, once before A and once before B. A function parameter is essentially a variable whose initial value will be supplied later when the function is called. Every function has an executable part called the body, which is enclosed in the braces. The body of average consists of a single return statement. Executing this statement causes the function to return to the place from which it was called. The value of a plus b over 2 will be the value returned by the function. To call a function, we write the function name, followed by a list of arguments. For example, average x, y is a call of the average function. Arguments are used to supply information to a function. In this case, average needs to know which two numbers to average. The effect of the call average xy is the copy. The effect of the call average xy is to copy the values of x and y into the parameters a and b, and then execute the body of average. An argument doesn't have to be a variable. Any expression of a compatibility type will do. Any expression of a compatible type will do, allowing us to write average 5.1, 8.9, or average x over 2, y over 3. We'll put the call of average in the place where we need to use the return value. For example, we could write printf average is %g \n, call to average xy, to compute the average of xy and then print it. This statement has the following effect. The average function is called with x and y as arguments. X and y are copied into a and b parameters. Average executes its return statement, returning the average of a and b. Printf prints the value of average, returns. The return value of average becomes one of printf's arguments. Note that the return value of average isn't saved anywhere. The program prints it and then discards it. If we need the return value later in the program, we could have captured it in a variable, such as average equals to average of x, y. This statement calls average, then saves its return value in the variable avg. Now, let's use the average function in a complete program. The following program reads three numbers and computes their averages one pair at a time. Enter three numbers: 3.5, 9.6, 10.2. Average of 3.5 and 9.6, 6.5. Average of 9.6 and 10.2, 9.9. Average of 3.5 and 10.2 is 6.85. Among other things, this program shows that a function can be called as often as we need. Average.c computes a pairwise average of three numbers. Include standard IO.h. We define a double average, double A, and double B parameters, which returns the average, which is a plus b over 2. We then have a main function, which takes in three double values, x, y, and z. We call printf to enter these numbers and scan them into the values of x, y, and z. We then compute the average using the call to average for the pairwise averages of x, y, and z, and return 0. Notice that I put the definition of average before main. We'll see in section 9.2 that putting average after main causes problems. Program printing a countdown. Not every function returns a value. For example, a function whose job is to produce output may not need to return anything. To indicate that a function has no return value, we specify that its return type is void. Void is a type with no values. Consider the following function, which prints the message t minus n and counting, where n is supplied when the function is called. Void print count int n. Printf t minus %d and counting, and put in the value of n. Printf print count has one parameter, n, of type int. It returns nothing, so I've specified void as the return type and omitted the return statement. Since print count doesn't return a value, we can't call it in the same way we call average. Instead, a call of print count must appear in a statement by itself, such as print count of I, semicolon. Here's a program that calls print count 10 times inside of a loop. Countdown.c prints a countdown. We include standard I/O. We have a void return of print count function, which takes in an integer. We then print this statement, inserting the integer into the print statement. We then, in the main function, have int I for I up to 10. For I equals to 10 up until I is 1 inclusive. We're going to print the value of I and reduce it each time, 10, 9, all the way to 1. Initially, I has the value of 10. When print count is called for the first time, I is copied into n, so that n takes on the value 10 as well. As a result, the first call of print count will print t minus 10 and counting. Print count then returns to the point at which it was called, which happens to be the body of a for statement. The for statement resumes where it left off, decrementing I to 9 and testing whether it's greater than 0. It is, so print count is called again, and this time printing t minus 9 and counting. Each time print count is called, I is different, so print count will print 10 different messages. Printing a pun revisited. Some functions have no parameters at all. Consider print pun, which prints a bad pun each time it's called. Void print pun void. So this function has no parameters and no return type. Printf, to see or not to see, that is the question. So it's just a single print statement. The word void in the parentheses indicates that print pun has no arguments. This time we're using void as a placeholder. That means nothing goes here. To call a function with no arguments, we write the function's name followed by parentheses, print pun, parentheses, parentheses, semicolon. The parentheses must be present even though there are no arguments. Here's a tiny program that tests the print pun function. Here's a tiny program that tests the print pun function. Pun2.c prints a bad pun. Include the standard I/O. Void print pun void. We print that pun within this print pun function. In the main function, we call the print pun and then return 0. The execution of this program begins with the first statement in main, which happens to be a call of print pun. When print pun begins to execute, it in turn calls printf to display a string. When printf returns, print pun returns to main. Function definitions. Now that we've seen several examples, let's look at the general form of a function definition. Return type, function name, parentheses, parameters, parentheses, curly brace, declarations, statements, curly brace. The return type of a function is the type of value that the function returns. The following rules govern the return type. Functions may not return arrays, but there are no other restrictions on the return type. Specifying that the return type is void indicates that the function doesn't return a value. If the return type is omitted in C89, the function is presumed to return a value of type int. In C99, it's illegal to omit the return type of a function. As a matter of style, some programmers put the return type above the function name. Double average. Interesting. Putting the return type on a separate line is especially useful if the return type is lengthy, like unsigned long int. After the function name comes a list of parameters. Each parameter is preceded by a specification of its type. Parameters are separated by commas. If the function has no parameters, the word void should appear between the parentheses. Note, a separate type must be specified for each parameter, even when several parameters have the same type. Double average, double a, comma, b is wrong. The body of a function may include both declarations and statements. For example, the average function could be written as so: double average, double a, comma, double b, we have a declaration of double sum where we cause sum to be the sum of a plus b and then divide the value of sum by 2 and return that value, having a declaration and two statements. Variables declared in the body of a function belong exclusively to that function. They can't be examined or modified by the other functions. In C89, variable declarations must come first before all statements in the body of a function. In C99, variable declarations and statements can be mixed as long as each variable is declared prior to the first statement that uses the variable. Some pre-C99 compilers also allow mixing of declarations and statements. The body of a function whose return type is void, which I'll call a, quote, void function, can be empty. Leaving the body empty may make sense during program development. We can leave room for the function without taking the time to complete it, then come back later and write the body. Oop. Thanks so much. Who was that? Salty Sponge. Appreciate the sub. You're awesome. I'm actually going to, unfortunately, have to turn off the alerts here, just for the time being. So while I'm recording here. Hey, how's it going, Brandon? Welcome in. How's it going, Augie? Learning C, and welcome. I'm learning Kotlin. Nice. That's awesome, man. All right, cool. Leaving the body empty may make sense during program development. We can leave room for the function without taking the time to complete it, then come back later and write the body. This section is long. Function calls. A function call consists of a function name followed by a list of arguments enclosed by parentheses. Average x, y, print count I, print pun. If the parentheses are missing, the function won't get called, such as print pun semicolon, which is wrong. The result is a legal, albeit meaningless expression statement that looks correct, but has no effect. Some compilers issue a warning such as a, quote, statement with no effect, close quote. A call of a void function is always followed by a semicolon to turn it into a statement. Print count takes in I as a parameter, semicolon. Print pun takes in nothing as the parameters, semicolon. A call of a non-void function, on the other hand, produces a value that can be stored in a variable, tested, printed, or used in some other way. We can average equals to average of x, y. If this computed value is greater than 0, then print the average is positive. And then we can say the average is this. The value returned by a non-void function can always be discarded if it's not needed. Average x, y discards the return value as we're not saving it in a variable. This call of average is an example of an expression statement, a statement that evaluates an expression but then discards the result. Ignoring the return value of average is an odd thing to do, but for some functions it makes sense. The printf function, for example, returns the number of characters that it prints. After the following call, numchars will have the value 9. Numchars equals to printf, quote, hi, comma, mom, exclamation mark, backslash n, close quote. If we print the numchars, we'll have a value of 9, it sounds like. I didn't know that. Since we're probably not interested in the number of characters printed, we'll normally discard printf's return value by just calling printf by itself with no variable saving. To make it clear that we're deliberately discarding the return value of a function, C allows us to put void before the call. Parenthesis void, parenthesis printf. What we're doing is converting the return value of printf to type void. In C, casting to void is a polite way of saying throwing away. Using void makes it clear to others that you're deliberately discarding the return value, not just forgot that there was one. Unfortunately, What we're doing is converting the return value of printf to type void. In C, quote, casting to void, close quote, is a polite way of saying, quote, throwing away, close quote. Using parenthesis void, parenthesis, or casting void makes it clear to others that you deliberately discard the return value, not just forgot that there was one. Unfortunately, there are a great many functions in the C library whose values are routinely ignored. Using parenthesis void, parenthesis, when calling all them can get tiresome, so I haven't done so in this book. Program, testing whether a number is prime. To see how functions can make programs easier to understand, let's write a program that tests whether a number is prime. The program will prompt the user to enter a number, then respond with a message indicating whether or not the number is prime. Enter number 34, not prime. Instead of putting the prime testing details in main, we'll define a separate function that returns true if its parameter is a prime number and false if it isn't. When given a number, n, the isPrime function will divide n by each of the numbers between 2 and the square root of n. If the remainder is ever 0, we know that n isn't prime. Test whether a number is prime. Include standard bool and include standard IO. We define a isPrime function which returns a boolean and takes in an integer. We have a declared int divisor. If the n provided is less than or equal to 1, we return false. For divisor equals to 2, divisor times divisor is less than n, or equal to n. For divisor is equal to 2, the square of divisor is less than n. Sorry, I keep saying this wrong. For divisor is equal to 2, and divisor times divisor is less than or equal to n, we're going to continually increase the divisor value. If the remainder of n divided by the divisor is 0, we're going to return false, else we're going to return true at the end of the loop, if we ever encountered one. Int main void. Int n, printf, enter a number. Scanf, we're going to read that number into n. If is prime on n, printf prime, else printf not prime, return 0. Notice that main contains a variable named n, even though is prime's parameters is also named n. In general, a function may declare a variable with the same name as a variable in another function. The two variables represent different locations in memory, so assigning a new value to one variable doesn't change the other. This property extends to parameters as well. Section 10.1 discusses this point in more detail. As isPrime demonstrates, a function may have more than one return statement. However, we can execute just one of these statements during a given call of the function, because reaching a return statement causes the function to return to where it was called. We'll learn more about the return statement in section 9.4. Cool. That was a long section here. So we got quite a bit of notes to go back and take here, but I think we'll be rather quick, as this is a lot of review. Okay, so here we go. So computing function definitions. Suppose we need to compute average type of doubles. Define your own, what it would look like. So let's just take this. We'll take this image here. Remember, if you guys want access to these notes, they're just in my GitHub repo link down below, so you can find them there pretty easy. We'll get out of here. The word double at the beginning is the average return type. So we'll say the word double at the beginning is the function's return type. The data of the function return type is each time as it's called. The identifiers A and B. Okay, here we go. The identifiers A and B, the function's parameters represent the two numbers that will be supplied when average is called. Each parameter must have a type, right? Each parameter must have a type. In this example, both A and B have type double. Nice. Every function has an executable called the body. Every function has an executable part called the body, which is enclosed in braces, which is enclosed in braces. The body of the average consists of a single return statement. Executing this statement causes the return. A body may contain a return statement. Executing the statement causes the function to return to the place from which it was called. I like that. We'll take that. To call a function, we must write the following arguments. Blah, blah, blah. Okay. So let's say you can call the function it's kind of as is, right? No, I guess we'll just go like this. Ooh. We'll take this picture here, take this guy, copy this into here. All right, we'll say that you can, if needed, we can save the value returned from functions within a variable. Okay, cool. Nice. And then printing countdown, let's see, remain. That's fine. Can as well parameter type in. So return type of void. Okay, so we'll say void return type. For example, a function whose job it is to produce output may not need to return anything. To indicate that the function has no return value. May not return anything. Output. Whose job it is. A function whose job who does not return anything. The job is completed, whatever. That's fine. Make it simple. So you can do void as the definition here. Cool. Print countdown is one parameter type int. Right, cool. Fine. As a value of 10, it goes down, t minus 10. Print countdown returns the point which was called. Just explaining the loop, which is pretty what we've learned already about. And then we have pun revisited, which is void. Have no parameters at all. We'll say void parameters, right? Some functions have no parameters at all. A function that has no parameters can be defined using void within the kind of like that, yeah. And then we'll just take this guy here. Nice. The word void in parentheses indicates the print point has no arguments. Yep, we got that. Must be present. That's fine. Okay, function definitions. Here we're just kind of updating our notes. That's after we finish this section of reading. So this is function definitions. So let's take this guy here, copy him into here, and then we'll go and make the return type function that is the type of the value the function returns. Following rules govern the return type. Rules governing return types of functions. 1. Functions may not return arrays, but there are no other restrictions on the return type. 2. Specifying that the return type is void indicates that the function doesn't return a value. 3, if the return type is omitted in C89, the function is presumed to return a value of type int. In C99, it's illegal to omit the return type of a function. Okay. I guess I'll say function return types can be given on the line above a function definition or declaration. Okay. All parameters must have a return type despite similar types used prior. The same, despite if the same type of this type. Okay. Cool. We can have declarations and statements. That's fine. Void can be empty. Whatever. It's fine. We don't really. It's not that important, but it's whatever. Cool. It's just more review over that what we kind of went over here. The call is always followed by semicolon. Cool. Discards the value. Yeah, some functions return values. So say I'm gonna go here and I'll say functions that return a value that we want. Oh, let's go like this. Let's put this down here. Functions that return a value that we want to ignore we can not use. We cannot use a variable, or we can specify, we can cast void to the function as a indicator that we are purposefully ignoring a return value. Something like this. Let me go ahead and get a little bit of feedback on this verbiage. Open this thing up. Let's get some feedback here. If function returns a value, just say clean this up. If a function returns a value that we intentionally want to ignore, we can either avoid assigning it a variable or explicitly cast the function call to void. Yeah, like that. Okay, perfect. We'll put this here. Nice. And so the example will say printf returns the number of characters printed. Often this is ignored and not saved in a variable. We could do the following, right? And take this here like such. Okay. Nice. All right, let's keep pushing. And this is just an example, which returns a Boolean function. Cool. All right, I think that does it. So that is some good notes for 9.1. So make sure you go check those out if you want to. Link down below in the GitHub, or you can find them in my Discord for free. Everything is for free in the community. All right. Let's go ahead and do 9.2 here, function declarations. Okay. Make sure we're recording, right? Yep, good. Hey, Agent 03, what's going on? Welcome in. Okay. 9.2, function declarations. In the programs in section 9.1, the definitions of each function was always placed above the point at which it was called. In fact, C doesn't require that the definitions of a function precede its calls. Suppose that we rearrange the average.c program by putting the definition of average after the definition of main. Include the standard IO into main void with the function there. And then we, after the main function, we have the double average function. When the compiler computes the first call of average in main, it has no information about average. It doesn't know how many parameters average has, what the types of these parameters are, or what kind of values average returns. Instead of producing an error message, though, the compiler assumes that average returns an int value. Recall from section 9.1 that the return type of a function is int by default. We say that the compiler has created an implicit declaration of the function. The compiler is unable to check that we're passing average the right number of arguments and that the arguments have the proper type. Instead, it performs the default argument promotions and hopes for the best. When it encounters the definition of average later in the program, the compiler notices that the function's return type is actually double, not int, and so we get an error message. One way to avoid this problem of call before definition is to arrange the program so that the definition of each function precedes all its calls. Unfortunately, such an arrangement doesn't always exist, and even when it does, it may make the program harder to understand by putting its function definitions in an unnatural order. Fortunately, C offers a better solution. Declare each function before calling it. A function declaration provides the compiler with a brief glimpse. Fortunately, C offers a better solution. Declare each function before calling it. A function declaration provides the compiler with a brief glimpse at a function whose full definition will appear later. A function declaration resembles the first line of a function definition with a semicolon added at the end. Needless to say, the declaration of a function must be consistent with the function's definition. Here's how our program would look with a declaration of average added. We include standard IO. We have a declaration before the main function of double average, which has parameters of double A and double B. We then have our main function, and then we have our average function below. Function declarations of the kind we've been discussing are known as function prototypes to distinguish them from an older style of function declarations in which the parentheses are left empty. A prototype provides a complete description of how a call to a function, how many arguments to supply, what their type should be, and what type of result should be returned. Incidentally, a function prototype doesn't have to specify the names of a function parameters. Sorry, I'm going to go back. I messed up there. Function declarations of the kind we've been discussing are known as function prototypes. To distinguish them from an older style of function declaration in which the parentheses are left empty, a prototype provides a complete description of how to call a function, how many arguments to supply, what their type should be, and what type of result will be returned. Incidentally, a function prototype doesn't have to specify the names of the function parameters as long as their types are present. Double average double double isn't usually best. It's usually best not to omit parameter names since they help document the purpose of each parameter and remind the programmer of the order in which arguments must appear when the function is called. However, there are legitimate reasons for omitting parameter names, and some programmers prefer to do so. C99 has adopted the rule that either a declaration or definition of a function must be present prior to any call of a function. Calling a function for which the compiler has not yet seen a declaration or definition is an error. 9.3 arguments. Okay, cool. That wasn't that long. 9.2 was pretty short. What's up, Guppy? How's it going? Yeah, I've looked at the Handmade Hero stuff. It's kind of useful At the beginning is I've yet to get through the beginning part into the actual weeds of the code stuff because it takes quite a while to get set up into the Windows environment, and I don't ever use Windows besides to play a couple video games. So, but I could probably watch a little bit more and get into the weeds of it for sure. Yeah. Often was kind of wanting more like raw hands-on learning stuff like that, so I kind of started doing it myself. Okay, let's go and take some notes on 9.2 that we just finished up here. This is the read-along of C Programming: A Modern Approach 2nd Edition by K.N. King of Chapter 9, Functions. We've been reading this book live on stream as I've been teaching myself computer science and programming from the ground up here after my 9 to 5 job as a chemist and on weekends. I have a degree in human biology and a minor in chemistry. I'm 26 years old. I've been doing this for about a year and a half now. We started with Python. We have cool projects in Python. I've gained some good kind of fluency in Python, and we have the ability to kind of pick up some stuff pretty quickly in there. And now we're kind of moving on to C to be able to learn what is actually going on in Python and dive deeper into programming and computer science as a whole. So thanks so much for being here. If that sounds interesting to you, or just kind of studying along with somebody on kind of a daily basis, consider following along here. A lot of people just use the stream to kind of put in the background to hold themselves accountable because they oftentimes have difficulty, being steadfast in your studies. So use it to your advantage. You don't have to be like directly listening to what we're doing, but you can just kind of get some computer science in the background while you're doing whatever you're doing. Okay, cool. So this talks about definitions of a program, and the program, the definition is always placed above, blah, blah, blah. Compile average after main, doesn't know, it tries to fill. So this just talks about how it tries to kind of, so we'll do this definition here of implicit declaration. When a compiler tries to, when a compiler infers, assumes that a function returns an int, or the order in which order/types of the parameters due to the function not being defined prior to being read/used. Let's get some feedback here. This is like in modern C, implicit functions are not allowed. So revise. When a function is used without a proper or prior type, causing older C compilers to assume it's returning an int. In modern C, it's illegal, results in compilation error. When an older, we'll say C89 compiler assumes that a function returns a type in order. Modern, we'll say modern C99 compilers will throw a compile right. Okay, cool. Nice. It is to call before the definition. a function declaration, right? Okay, so we have function declaration provides the compiler with a brief glimpse of a function at a glimpse that we'll see later. Okay, then we'll take this, like so. I like that definition. Provides the compiler with a brief glimpse at a function whose definition will appear later. A function declaration resembles the first line of a function definition with a semicolon at the end, like so. Bum, 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 dun, dun, dun. Nice. Needless to say, consistent with the declaration here. Function declarations of the kind we've been using are known as function prototypes, aka quote function prototypes. Right, also known as function prototypes. A prototype provides a complete description, right? We'll take this. Of how to call a function. How many arguments to supply, what their type should be, and type which will be returned. Like that, and then we'll bring that back. Here we go. Nice. Then we'll also say function prototypes don't have to specify their names of the functions. The names of the function. As long as their types are present. Okay, like so. Cool. Nice. Sweet. Thanks, AJ. I appreciate the kind words. Thanks so much for stopping in and joining me here. You're awesome. Let's go ahead and button up this one. Yeah, we got a cool couple of Python projects we wrote on the channel. We wrote some more full stack projects with a Python backend and Python scripts such as SpectroSim and ChromaPlot, which are some biochem kind of a chemistry spectroscopy, absorption spectroscopy, and paper chromatography simulators. They're kind of like undergraduate laboratories that you do to get your kind of biology and chemistry degrees. I kind of simulated those using programming and using front end visuals to kind of mimic that chemical movement, and then also the graph outputs using kind of absorption spectroscopy devices using pre-existing data pulling from a PubChem API, which is a large online chemical database, which is really cool. We also have built, we're building some more projects, kind of actual projects related to our small business, Better Linen, which is a kind of small rehoming business for vintage clothing that we find and source locally, and provide to our customers at a very affordable rate for recycling and kind of a hobby of ours. We built a custom scraper to actually write over our or read over our Depot page and link those up to a current standing of products, and we kind of built a process flow map for a product life cycle in Python and how it should be kind of handled. And then it's kind of linked up to a React front end that we've been building live on the channel. So go check out those streams. Everything I've been doing building is live. I rarely ever do coding off stream. I maybe do about 5% of my coding, 10, maybe less than 10% of coding off stream, 90 to 95% on stream, and I'd say about 98 to 99% of the coding I do is all my own. It's not vibe coding. It's not AI. We do use AI to get help and to refine our understanding and learning, but the coding itself that we do is original. I like that aspect, and I like being original and coming up with our own ideas, and it's fun that way. We're not in any rush to grind through this for any other thing. We're just kind of learning for fun and getting an audience and getting some friends here along the way. So welcome everybody. Nice. Let's go ahead and move on here. So those notes for section 9.2 are completed. 9.3 arg humans. Get some water. Thanks for coming in, Guppy. Paradox, is this your first time learning programming? We've been doing this for about a year and a half. Yeah, we've been learning Python before this, but this is been going into C a little bit deeper here. A lot of work so far. 8 chapters so far of exercises and programming projects of robust kind of beginner C programming knowledge. So really getting our bearings in order here and making sure that we're getting a good solid foundation in C basics. Okay, which is what we did in Python. We read the Python crash course book, and we've been going back through that and actually re-uploading and resolving the in-text practice problems and uploading those to the channel for you guys to get some additional practice with. Okay, let's keep pushing here. Chapter 9, 9.3, arguments. Let's review the difference between a parameter and an argument. Parameters appear in function definitions. They're dummy names that represent values to be supplied when the function is called. Arguments are expressions that appear in the function calls. When the distinction between arguments and parameters isn't important, I'll sometimes use argument to mean either. In C, arguments are passed by value. When a function is called, each argument is evaluated and its value is assigned to the corresponding parameter. Since the parameter contains a copy of the argument's value, any changes made to the parameter during the execution of the function don't affect the argument. In effect, each parameter behaves like a variable that's been initialized to the value of the matching argument. The fact that arguments are passed by value has both advantages and disadvantages. Since a parameter can be modified without affecting the corresponding argument, we can use parameters as variables within the function, thereby reducing the number of genuine variables needed. Consider the following function, which raises a number x to power n. Int power, which takes in int x and int n. We declare int I and int result, which equals to 1. For I equals to 1, while I is less than or equal to n, I plus plus, result equals to result times n. Return result. Since n is a copy of the original exponent, we can modify its inside the function, thus removing the need for I. Int power, int x, int n, int result equals to 1, while n less than is greater than 0, result equals to result times n. Unfortunately, C's requirement that arguments be passed by value makes it difficult to write certain kinds of functions. For example, suppose that we need a function that will decompose a double value into an integer part and a fractional part. Since a function can't return two numbers, we might try passing a pair of values. Since a function can't return two numbers, we might try passing a pair of variables to the function and having it modify them. Void decompose, which takes in double x, long int part, and double frac part. Int underscore part equals to long cast of the x variable, which drops the fractional part. Frac part equals to x minus the integer part, which just leaves the decimal portion. Suppose that we call the function in the following way. Decompose pi, which is 3.14159, I, and d. At the beginning of the call, 3.14159 is copied into x, which is a double. I's value is copied into int part, and d's value is copied into frac part. The statement inside decompose then assign 3 to int part and 0.14159 to frac part, and the function returns. Unfortunately, I and d weren't affected by the assignments to int part and frac part, so they have the same values after the call as they did before the call. With a little extra effort, decompose can be made to work, as we'll see in section 11.4. However, we'll need to cover more of C's features first. So this function, void decompose, takes in a double x, an int part variable, which is a long, and a frac part variable, which is a double. We overwrite the value of int part to be the casting of long to the variable x, which drops the fraction and saves the whole value of the double into int part. Oh, interesting, right? Because we're passing by direct value here. We're actually passing the physical value of double x and int part and frac part. Now int part and frac part may not be, initialized anywhere, and they could just be, dummy values or trash values in memory until they're actually overwritten here in this function call, in this body. But we're actually modifying those copied values in the function, and we're just leaving them there. We're not doing anything, right? And so I think this is alluding to the fact that we will need pointers to pass in the reference of the variable in order to modify that actual value within the program and not have to copy it into the function, modify it, return it, and copy it out back, right? We can just reduce that by passing in the pointer to the memory location directly, have the work be done on the value at that pointer, and then return success, right? Yeah, that's probably what it's getting to. Cool, I'm glad that we were able to kind of see what it's getting to here. So just to recap, what it's kind of alluding to here is that these function parameters during this definition of this decomposed function, when you call this and you supply the function with arguments, which it then fills in as the parameters, right? They're kind of interchangeable, but it's kind of just perspective of how you're using the function, whether you're defining it or actually using the function. You're putting stuff in for the parameters, which are the arguments, right? And so those arguments are being copied, their values, into the references, or sorry, into the parameters, and those parameters are having work done on them. In this function particularly, nothing is actually causing those original values or variables to have that work be saved on them, like what happens in Python automatically when you pass in an object into the function. That object kind of has a trailing memory effect. Okay, it's now here. It's now being it's now having work done on it here, and so you can cascade and basically pass in an object through many different functions to perform work on it directly rather than any memory of that object. All right. Okay, let's keep pushing. Argument conversions. C allows function calls in which the types of the arguments do not match the types of the parameters. The rules governing for how the arguments are converted depend on whether or not the compiler has seen a prototype for the function or the function's full definition prior to the call. The compiler has encountered a prototype prior to the call. The value of each argument is implicitly converted to the type of the corresponding parameter as if by assignment. For example, if an int argument is passed to a function that was expecting a double, the argument is converted to a double automatically, because we've already seen this kind of prototype blueprint ahead of time, and so the compiler knows to kind of do a conversion implicitly here. The compiler has not encountered a prototype call. The compiler has not encountered a prototype prior to the call. The compiler performs the default argument promotions. 1. Float arguments are converted to double. 2. The integral promotions are performed, causing char and short arguments to be converted to int. In C99, the integer promotions are performed. Relying on the default argument promotions is dangerous. Consider the following program. Include standard io.h, int main void. We declare a x variable, which is a double and has a value of 3.0. We printf square and insert the value of a function call square of x. So square, right, which is here, returns an int and takes in an int and returns that int times the int. Cool. At the time square is called, the compiler hasn't seen a prototype yet. There's no prototype above the main function before it's called, right? So it doesn't know that the square expects an argument of type int. Instead, the compiler performs the default argument promotions on x with no effect. Since it's expecting an argument of type int, but has been given a double value instead, the effect of calling square is undefined. The problem can be fixed by casting square's argument to the proper type. Printf, quote, square, %d \n, square, cast int onto x. Of course, a much better solution is to provide a prototype for the square before calling it. In C99, calling square without first providing a declaration or definition of the function is an error. Array arguments. Arrays are often used as arguments when a function parameter is a one-dimensional array. The length of the array can be, and normally is, left unspecified. Int f, which takes in an int array a. No length specified. The argument can be any one-dimensional array whose elements are of the proper type. There's just one problem. How will f know how long the array is? Unfortunately, C doesn't provide any easy way for a function to determine the length of an array passed to it. Instead, we'll have to supply the length, if the function needs it, as an additional argument. Although we can use the size of argument to help determine the length of an array variable, it doesn't give the correct answer for an array parameter. Int f takes in an array of type int. We say that the int length is equal to the size of a over the size of a index of 0. This is wrong. not the number of elements in A. Section 12.3 explains why. The following function illustrates the use of one-dimensional array arguments. When given an array of A of int values, sum array returns the sum of elements in the array A. Since sum array needs to know the length of A, we must supply it as a second argument. Int sum underscore array takes in an integer array A and a single integer value. We define a sum equals to 0 and declare an int I variable. Both of these are ints. For I equals to 0, while I is less than n, increase I. Sum will increase by the value of the array at index of I and return the sum at the very end. The prototype for sum array has the following appearance: int sum array, int A array, and int n. As usual, we can omit the parameter names if we wish. When sum array is called, the first argument will be the name of an array, and the second argument will be its length. For example, define len 100. We have a main function, and we call a variable b, which is an array of size length 100 and an integer total. We say total is equal to sum array given the array b and the length of len. Notice that we don't put brackets after an array name when passing it to a function. This is wrong. An important point about array arguments: a function has no way to check that we've passed it the correct array length. We can exploit this fact by telling the function that the array is smaller than it really is. Suppose that we've only stored 50 numbers in the B array, even though it could hold 100. We can sum just the first 50 elements by writing the 50 directly in for that parameter, with 50 as that argument, right? Sum array will ignore the 50 other elements. Indeed, it won't know that they even exist. Be careful not to tell a function that an array argument is larger than it really is, such as 150 in for that argument. In this example, sum array will go past the end of the array, causing undefined behavior. Another important thing to know is that a function is allowed to change the elements of an array parameter, and the change is reflected in the corresponding argument. For example, the following function modifies an array by storing 0 into each of its elements. Void stores zeros, takes in an array of integers and an integer n. We declare an int I for I equals to 0, while I is less than n I plus plus. We assign all the values in the array at index of I equal to 0. The call store underscore 0 of b 100 will store zeros into the first 100 elements of the array b. This ability to modify the elements of an array argument may seem to contradict the fact that C passes arguments by a value. In fact, there's no contradiction, but I won't be able to explain why until section 12.3. If a parameter is a multidimensional array, only the length of the first dimension may be omitted when the parameter is declared. For example, if we revise the sum array function so that A is a two-dimensional array, we must specify the number of columns in A, although we don't have to indicate the number of rows. So we define len to be 10. We have int sum two-dimensional array, which takes in an integer array A of addition of row columns length, and int n. Int I j sum 0 for I equals to 0, I less than n, I plus plus. We're going to, and then index, for I equals 0, I is less than n, I plus plus. For j equals to 0, j less than length, the columns, j plus plus. Sum plus equals to a index I, index j, return sum. Not being able to pass multidimensional arrays with an attribute number of columns can be a nuisance. Fortunately, we can often work around this difficulty by using arrays of pointers. C99's variable length array parameters provide an even better solution to the problem. C99 variable length array parameters. C99 adds several new twists to array arguments. The first has to do with variable length arrays, VLAs, a feature of C99 that allows the length of an array to be specified using a non-constant expression. Variable length arrays can also be parameters, as it turns out. Consider the sum_array function discussed earlier in this section. Here's the definition of sum_array with the body omitted. Int sum_array takes in an array A of integers and an int n. As it stands now, there's no direct link between n and the length of the array A, although the function body treats n as A's length. As it stands now, there's no direct link between n and the length of the array A. Although the function body treats n as A's length, the actual length of the array could in fact be larger than n, or smaller, in which case the function won't work correctly. Using a variable length array parameter, we can explicitly state that A's length is n. Int sum_array, int n, int A, array of n. The value of the first parameter, n, specifies the length of the second parameter, A. Note that the order of the parameters has been switched. Order is important when the variable length array parameters are used. The following version of sum_array is illegal, where we define the array before the length that we're using within the actual array declaration. The compiler will issue an error message at int a index n because it hasn't yet seen n. There are several ways to write the prototype for our new version of sum_array. One possibility is to make it look exactly like the function definition. Int sum_array, int n, int array, size of n, which is version 1. Another possibility is to replace the array length by an asterisk. Int sum_array, int n, int a array, size of asterisk. The reason for using the star notation is that the parameter names are optional in the function declarations. If the name of the first parameter is omitted, it wouldn't be sorry. The reason for using the star notation is that the parameter names are optional in the function declarations. If the name of the first parameter is omitted, it wouldn't be possible to specify the length of the array is n, but the star provides a clue that the length of the array is related to parameters that come earlier in this list. Int sum_array, int bracket star bracket. It's also legal to leave the brackets empty, as we normally do when declaring an array parameter. Int sum_array, int n, int array A, which is version 3a, and int sum_array, int array, version 3b. Leaving the brackets empty isn't a good choice because it doesn't expose the relationship between n and a. In general, the length of a variable length array parameter can be any expression. For example, suppose that we were to write a function that concatenates two arrays a and b by copying the elements of a followed by the elements of b into a third array named c. Int concatenate, which takes in int m, int n, an array of size m of integers, an array b of size n of integers, an array of size c of m plus n, an array c of size m plus n of integers. The length of c is the sum of the lengths of a plus b. The expression used to specify the lengths of c involves two other parameters, but in general, it could refer to variables outside the function or even call other functions. Variable length array parameters with a single dimension, as in all our examples so far, have limited usefulness. They make a function declaration or definition more descriptive by stating the desired length of an array argument. However, no additional error checking is performed. It is still possible for an array argument to be too long or too short. It turns out that the variable length array parameters are most useful for multi-dimensional arrays. Earlier in this section, we tried to write a function that sums the elements in a two-dimensional array. Our original function was limited to arrays with a fixed number of columns. If we use a variable length array parameter, we can generalize the function to any number of columns. Int sum two-dimensional array takes in int m. Int sum two-dimensional array takes in int n, int m, and an array of integers of size n by m. So we have integers I, j, and sum, which is equal to 0. We loop through I up through n and j through m, and we sum equals to the values at array index I, index j. Prototypes for this function include the following. Int sum two-dimensional array, which could be int n, int m, int a, n by m. We could do a asterisk asterisk. We could do just the m, and we could do asterisk just in the column itself. So really quick, the asterisk. But the asterisk still doesn't specify a size, though. Okay, I'm almost done with this section. Okay, C99, using static in array parameter declarations. C99 allows the use of the keyword static in the declarations of array parameters. The keyword itself existed before C99. Section 18.2 discusses its traditional uses. In the following example, putting static in front of the number 3 indicates that the length of A is guaranteed to be at least 3. Int sum array, which takes in an integer array size static 3, and int n. Using static in this way has no effect on the behavior of the program. The presence of static is merely a hint that may allow a C compiler to generate faster instructions for accessing the array. If the compiler knows that an array will always have a certain minimum length, it can arrange to prefetch these elements from memory when the function is called, before the elements are actually needed by statements within the function. One last note about static: if an array parameter has more than one dimension, static can be used only in the first dimension. For example, when specifying the number of rows in a 2D array. Compound literals in C99. Let's return to the original SumArray function one last time. When SumArray is called, the first argument is usually the name of an array, the one whose elements are to be summed. For example, we might call SumArray in the following way, where we have an array B, which has 3, 0, 3, 4, 1 within it. We have total equals to SumArray, which takes in B and 5. The only problem with this argument is that B must be declared as a variable and then initialized prior to the call. If B isn't needed for any other purpose, it can be mildly annoying to create it solely for the purpose of calling SumArray. In C99, we can avoid this annoyance by using a compound literal, an unnamed array that's created on the fly by simply specifying which elements it contains. The following call of some array has a compound literal shown in bold as its first argument, where total is equal to some array, where we have a casting of int array to this sequence. And then we have the 5. In this example, the compound literal creates an array containing the 5 integers 3, 0, 3, 4, and 1. We didn't specify the length of the array, so it's determined by the number of elements in the literal. We also have the option of specifying a length explicitly within the actual compound literal. Int 4 for the sequence 1921 is equivalent to int 1921. In general, a compound literal consists of a type name within parentheses, followed by a set of values enclosed by braces. A compound literal resembles a cast applied to an initializer. In fact, compound literals and initializers obey the same rules. A compound literal may contain designators, just like a designated initializer, and it may fail to provide full initialization, in which case any uninitialized elements default to 0. For example, the literal int 10 int array 10 of sequence 6 and 8 has 10 elements. The first two have the values of 8 and 6, and the remaining elements, for example, the literal int array 10 with a sequence of 8 and 6 has 10 elements. The first two values of 8 and 6, and the remaining have value of 0. The compound literals created inside a function may contain arbitrary expressions, not just constants. For example, we could write expressions for the values within the sequence, where I, j, and k are variables. This aspect of compound literals greatly enhances their usefulness. A compound literal is an L value, so the values of its elements can be changed. If desired, a compound literal can be made read-only by adding the word const to its type, as in const int array with a sequence of 5, 4. Interesting. Okay, cool. So that's finished up section 9.3 there. So we'll go back through on 9.3 and take some notes, and then that's where we'll probably wrap it up for tonight. All right, let's go back and catch up on some chats here. I like your approach to learning new skills and doing it while streaming. In the process, this inspires me to do something similar. Nice. That's awesome. I'm happy that you're getting some inspiration here and liking the approach. Thanks so much for being here. If you guys are new, if you guys could subscribe. I'm pushing for 5K subs soon, if you guys could. It's free and it means a lot. We're 6 subs away from 4,400 actually, so maybe we'll hit it before end of the stream today. We're almost going to end though. I stream myself almost every single day, learning and teaching myself computer science and programming. I do program every single day, even if I don't stream, but I do try my best to stream. If I don't, I'm either editing videos regarding programming, doing some side scripts, or whatnot. But yeah, I have a full-time job as a chemist, and I do this after my job. So trying to just gain new skills, stay fresh, stay sharp, and see if we can compound these into our current knowledge. So let's take some notes here. We're on C Programming: A Modern Approach, 2nd edition by K and King. We're learning C after we've been learning Python for a little over a year and a half. We're diving deeper into C and programming in general. So let's take some notes here on 9.3 that we just read from on functions, but more specifically arguments. So let's just make a definition: arguments. Arguments, parameters appear in function definitions. They're dummy values. Okay, so we'll go. Okay, like this. We'll take this. We'll go arguments versus parameters. And then we'll go like this and say parameters appear in function definitions or dummy names, values applied to function calls. And then arguments are these, right? The values filled in for those parameters in the function calls. In C, arguments are passed by values. So in C, arguments are passed by value when a function called each argument is evaluated and its value is assigned its corresponding parameter. Cool. Since the parameter contains a copy of the argument's values, any changes made to the element parameter during the execution of the function doesn't affect the argument. Right? That's important. So we're gonna highlight, define here. Any changes made to the contains a copy. The fact that it has advantages if it's passed by value can be modified with the corresponding argument. We can use parameters as variables. Unfortunately, C requirement that arguments be passed by value makes it difficult to write certain kinds of functions. Right, this is just, we've already taken notes on casting and stuff, so we don't really need to. Okay. Argument conversions. C allows function calls in which the type of arguments don't match the type of parameters. Right, yep. And then we're going to do these rules here. A compiler prior to the call. Like that, and then say the value of each argument is supposed to convert it to type. Yeah. Kind of speed running these notes here. We've been going for a little bit now. I'm kind of tired. And then for this one here. Prior to the call. The performs default argument promotions. 1 float. Arguments are converted to double. 2 the integral promotions are performed. Char and shor are converted to int. Int. Are performed. Okay. Nice. Converted to double. Okay. It's dangerous though, right? Because in this case you're putting it in an integer. You're actually giving it a double, which might remove the float value, right? Okay, array arguments. Okay, arrays are often used as arguments when a function parameter is one-dimensional array. So we'll say Um, um, we'll just say, yeah, arrays as arguments. So arrays can be passed as arguments to functions, but C does not know their length. Why is this wrong? I'm going to ask this. If C is passed by elements and you pass an array, why can't you do size of A over size of A index 0 to compute the length? Why must you give length as a param? You can't compute this only at the point where the array actually still exists as an array. Once you pass it to a function, it's no longer an array. So size of stops working the way you expect. Arrays are not passed by value in C. C is passed by value only. But arrays are a special case. What actually gets passed is not the array, it's a pointer to the first element. I think it said an array pointer. It talked about that here. It's pointer to the first element. Array to pointer decay. So inside the parameter, A is a pointer, not an array. Okay, so when arrays are passed as arguments to a function, it's a pointer to the first element in the array. So you don't know the actual size of the array. You can, I guess you know the size of the element. Size of the array A, okay, will be a pointer. So you have to dereference it and you get maybe like an integer if that's what it is, but okay, whatever. Oh, interesting. A is an array. A is a real array. A is a real array. Size of A is 10. Falls inside a function, inside a foo. A is treated as an int pointer. Size of A is the size of a pointer, which is the size of an int 8 byte, which is wrong. Calling size of on an array passed as a parameter measures the size of an array, a pointer, which is what? 8 bytes. Arrays can be passed as arguments to functions, but their length information is not preserved. Okay, that's fine. When an array is passed as a function, it decays to a pointer of the first element. The first element. Inside the function, the parameter is treated as a pointer, not an array. Yes. That makes good sense. Yep. Kind of just redefining our calling size of on an array parameter, therefore yields the size of a pointer, typically 8 bytes on a 64 bits. It's not the size of the original array. This is good stuff here. this work? Okay, cool. So then you can declare one-dimensional arrays into here, return the sum, and then you have a prototype. We can omit the names if you'd like. You can put in variables for the length in the correct order. You don't pass in the thing there. Okay, so let me just kind of get some screenshots here of this whole thing here, like that. That's a good one. Okay, like that. And then, okay, it's fine. An important point about array arguments: a function has no way but check if it's passed the correct length array. We can exploit this fact by telling the function if it's smaller. Be careful not to tell the function it's larger than it really is. The function is allowed to change elements of the array parameter. We know that, yeah, it's pretty simple. Because it's a pointer to the array. So although, remember, so it's kind of a little bit confusing, honestly, and that's a little bit the one gripe I guess I will say about the book so far. I really like the book, but I wish it would just bite the bullet and just get it over with. Just give me the pointers already. Like, stop kind of giving me this, oh, I'll get to it, but like I'm abstracting out and kind of mixing in pointers and stuff here and there, like with like char, star, like strings and stuff like that. Like, no, just give me the pointer information already. Just like get it over with. Rip the band-aid off. Like, you're trying to like ease me into it, but we're like 200 pages in already, um, and you're still trying to bait me with it for like another 2 chapters. Just do it. Anywho, um, yeah. So what we learned about arrays here is that the array, when you pass into the function, passes a pointer to the first element within the array. So we can actually modify those places with store the first elements their inability to modify. Yeah, pointers right here. Here it is again. I won't give it. I'll tell you why later. Then you can do multi-dimensional array stuff. Okay, so that's fine. I'm kind of being a little bit lazy, I guess, but um, I'll just do the big things that we need here. So then we have a variable length array parameters. C99 adds several new twists to array arguments. The first has to do with the variable length arrays, right? We know that. Parameters. Consider this sum array where we have sum array which takes in an array of integers and n. As it now stands, there's no direct link between these two. The body treats n as a's length, but we could do this. Right, we'll just go like this. Using variables to dynamically set the length of arrays used in function parameters. Use as function parameters. Go here and paste that in there. Nice. The value of the first parameter n, right? We need to specify it first. So just like we'll say note that the variable, note that n is initialized first before being used as a feature of the array declaration, array parameter. Note that n is initialized before being used as a feature of the array parameter declaration. Okay. Nice. You can write prototypes this way. You can write an asterisk this way. So let's take these two examples here. We'll say, I guess we'll say prototypes. All right, we kind of already talked about prototypes and arrays. Prototypes and array parameters. Something like that. The reason for using the star notation is the parameter names are optional in the function declarations. If the name of the first parameter is omitted, it wouldn't be possible to specify the length of n. Right. Okay. The reason for using the star notation is that parameters names are optional in function declarations. Thank you so much for the follow. I appreciate that. Who was that? Scruns, appreciate you. Thank you for following along on Twitch. You the boss. Oh, who's that? Oh, that was Scruns, I think. Oh, hold on. We'll bring back the alerts. Okay. The reason for using the star notation is that parameter names are optional in the function declarations. If the name of the first parameter is omitted, it wouldn't be possible to specify that the length of the array is n. But the star, the asterisk, provides a clue that the length of the array is related to the parameter that will come later in the list. So let me, I guess I'll paste in this image here. Oh. Like there. And then we'll make this be that. And then we'll go like this and do these guys. So, nice. All right, cool. Don't really need to use that. It's pretty self-explanatory. You can use variable length arrays and stuff. So then I guess what we'll do is we'll give a general example here. And then I'll take this kind of a large image here of all this. This is pretty good. This is a really good like general example. Okay. So then we have static here. Almost done with this section, then we'll wrap it up. So using static in array parameter declarations. C9 allows use of static, right? If you guys missed the reading, just rewind back a couple minutes to the reading. We're just kind of skimming back through and adding some notes here. Static declarations for array parameters. The keyword existed itself before C9. You can do this. In the following example, putting static in front of the number indicates the length is carried. Okay. Putting static in front of the number, in front of the array I guess we'll do this. For these three, we'll take a picture of this. Copy image, put this there. Leave that, okay. And then what we'll say is using static has no effect on the behavior of the program. The presence of static is merely a hint to allow the faster accessing the array. Yeah, that sounds good. Use of static. Let's take this and get rid of this guy and this guy. If the compiler knows the array will have a certain minimum length, it can arrange to prefetch. This is kind of important too. I'm actually gonna. This is kind of fun little C like information. Kind of seems like a lot, I know, but I do want to have it. This is kind of fun. It's got like a fun fact. Okay. So then we'll also say an array parameter has only more than one length technically used in the first dimension. If and we'll say multi-dimension static can only be applied to the first dimension of the array. Okay, last section here for this, so compound literals. Let's return to the original summary function. When this is called, we can do this. The only problem with this arrangement is that b is declared as a variable, and since part of the call is not needed, we can do blah, 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 blah. We can, using a compound literal, right? So compound literals are an unnamed array that's created on the fly simply by creating the elements it can, specifying the elements it contains. Cool, my itchy chin. It's the following call for some reason, so it would be like this. Ooh. That. Takes 5 integers. We didn't specify the length, so it's determined by the number of elements in the literal. You can also specify the length. You can also specify the length by cool. Cast to initializer, nice. It's all zeros, cool. We know that by default. You can use expressions, and nice. So compound literals are, these are L values. the values of its elements can be changed. You can make it read only by adding const. Nice. All right, you guys. Cool. How long do we have still? So 9.4 is on just starting at 202. 9596. And then Q&A. Oh, we're pretty close. All right, well, tomorrow's stream we'll finish up chapter 9 reading then. Let's go ahead and push this up to GitHub. If you guys want access to these notes, they're just on my GitHub. So start chapter 9. Cool. Yeah, so they're up on my GitHub, so you guys can get access to these notes. Link down in the description below. This is C Programming: A Modern Approach, 2nd edition by K.N. King. We read chapter 9, 9.1, 9.2, and 9.3, and took some really good notes on them. Make sure to join back tomorrow, and we'll continue on with 9.4, the return statement, and continue on and finish the chapter up. Let me go ahead and I'll stop my recording here. I think we're good, right? Hey guys, come on. Yeah, we'll stop the recording here. Nice. There we go. Let's catch up on some chats here. Looking for fun is honestly the best way to learn because you don't force yourself to understand, rather let it naturally happen for me. Nice. I really like your approach. Oh, I read that one. Bro, Michael, have you been staying with coding, please? How has it been going for you? How have you been, bro? How have you been staying with the coding? Pla HW, has it been going for you? Hey, dude. Thanks, Armando, for the comment. It's been going good. Thanks for joining me. I recently graduated with an MS in Power, Electrical Engineering, and potentially pursue a doctorate. Nice, man. Recently been developing a passion for electronics, building embedded systems. So I'll try to follow your footsteps, maybe building something while streaming the process. Thanks for subscribing, Agent. All right, you guys. Thanks so much for being here and joining me tonight. I really appreciate everybody being here. This was a lot of fun as we read through the first probably a little over half of chapter 9 from C Programming: A Modern Approach, 2nd edition by K.N. King. If you guys are wanting to get access to the notes, they're on my GitHub. I also have a complete kind of video series breakdown on my channel where I have like the audiobook chopped up without any note taking or breaks or pauses or whatnot. So if you want to just listen to the book straight of the audio, kind of an audiobook format, you guys can do so on the channel. Make sure you guys subscribe. We're only 6 subscribers away from 4,400. So if you guys aren't subscribed, if you guys can please do so. We're only 6 away from 4,400. All right, guys. Thanks so much for being here. I'll see you guys tomorrow. I'll be back tomorrow. We'll continue on. Have a good night, guys. Peace out.